Now we will introduce reinforced concrete beams. Beams made of concrete should have special treatment. In fact, concrete is weak in tension, so it can sustain compression but not tension. This is why concrete beams that are subjected to bending moments should be reinforced by steel rods. In fact, the steel rods can carry a tensile load, while the concrete will be able to carry the compressive load. And this is why, for example, if we are subjecting the section to a positive bending moment, then the upper part will be subjected to compression, and this compression will be supported by the concrete material, while lower part will be subjected to tension. And since concrete is weak in tension, what we do is that in the lower part, which will be subjected to tension, we reinforce concrete by putting steel rods. Now, how to model this? In fact, we consider that concrete cannot sustain tension. It can just sustain compression. This is why we model our system as if we have a neutral axis. Above the neutral axis, we know that for a positive bending moment, you will have compression. So the concrete part will sustain the compression. However, since concrete is weak in tension, it cannot support tension, then in the lower part, we consider that concrete will not do any effect. It's not present here to sustain tensile effects. And then we consider that below the neutral axis, we just have steel. And this is why, as you can see in this figure, below the neutral axis, we have an empty part here, and we just consider the steel rods. Now, we can model the steel rods by a very thin, if you want, area, okay? So you can consider that this thickness is very small, negligible, okay? And you have the value of your area. So you have like a very long area here, okay, of negligible thickness and large value of length, in a way that uh, this area will represent the area of steel. But as we discussed before, whenever we have two different materials, we should convert the section. So instead of dealing with, if you want, just here the area of steel, we should multiply it by n. So we can calculate the equivalent area of these steel rods first, AS. So you know that, for example, for a circular cross section, let's say here you want to add three rods, okay? So the area A steel will be equal to 3 times pi d square over 4, okay? And then when you want to transform the whole section to one material, to be able to do the analysis as we did in previous examples, then we should multiply this area to convert, if you want, then to an equivalent section made of one material, okay? We should multiply this area by n, which is the ratio of elasticity modulus of steel over elasticity modulus of concrete. And then the modified section will consist on the following. It will consist on two parts. The first part is the part above the neutral axis made of concrete. And the lower part is the modified area, transforming steel area into an equivalent concrete area that is equal to n times AS. Now, whenever you have your modified section, you can continue the analysis. Okay? Now, one of the challenges is to determine where is my neutral axis. So we know that the neutral axis in general, okay, is defined as the level where you don't have stresses. So it's zero stress at this level, and you have that above the neutral axis for positive bending, you have compression, and below it you have tension effects. So here, in order to locate the neutral axis, we want to perform analysis. We know that from previous studies, when we do the modified section, the neutral axis should pass by the centroid of the modified section. And this is why we can consider that x bar, and if you want y bar, because we are doing the analysis of the position of the neutral axis along y direction. Okay, so y bar of the neutral axis is 0 in case we consider that the reference of y is along the neutral axis. Okay, so here we decided to say we don't know where is the neutral axis, we want to find its location. So we'll take a line, this line is the neutral axis, we'll consider it as the origin of a vertical axis y. Okay, since the centroid is the origin, and we know that if you want the neutral axis should pass by the centroid of the modified section, then what we will do is we will set y of c is equal to 0 is equal to y bar of the section. And how to calculate y bar of a section? You know that y bar is equal to summation of ai yi over a total. So since we are considering the y coordinate system, if you want origin on neutral axis, then we know that y bar should be equal to 0. And we want to find what is the x value, which is the level at which the neutral axis is below the top of the beam, in order to determine the position of the neutral axis. Because the challenge here is that I don't know x. Okay, so I don't know where is my neutral axis. I want to find it. I want to find the location of my neutral axis. I will use the property of the neutral axis, that the neutral axis should pass by the centroid of the modified section. Since I know this information, I will say it's true that I don't know where is the location of neutral axis, so this is why I will call the distance from the top level to the neutral axis as x. I want to calculate x. I need an equation for x. To write this equation, I say I will profit from my knowledge that the neutral axis is passing by the centroid of the modified section. So let me take a y vertical axis passing by this centroid, and then I know that y bar of this modified section should be equal to 0 because it is on the neutral axis. And by using the formula of what is y bar, it's summation of ai yi over a total. I did use that for this section. I should have that sum of ai yi equal to 0 because I selected the origin of my y-axis on the neutral axis. This equation will allow you to calculate x, because if you take the following example here, x is unknown, I want to find it. I say I have two areas, the area above the neutral axis and the area below the neutral axis. And below the neutral axis, as we discussed, we just consider the modified area of steel, because concrete is not able to sustain any compression. So we put an empty space here. We don't have anything. Okay, so I just have two areas, and their centroid is located here at this level, corresponding to y equal to 0. So I first write a 1y1 and plus a 2y2 equals to 0. Now I replace. First, what is a1? If I look at my figure, I named this distance x, and the width here is b. So a1 is b times x. What is y1? y1 is the centroid position of area 1. It's located at half of x from the neutral axis, so it's x over 2. So this is y1, x over 2 is y1, and b times x is a1. Now for the second term, plus a2 is the modified area, which is n times total cross-sectional area of steel, times, because a2 is below the neutral axis, then y2 is negative, and we know that, as you can see here, we don't know where is the neutral axis. So we just consider, we need to find x here. What is x? We can express the distance from neutral axis to the center of the steel rod as you can see, the distance between the top of the beam and the center of the steel rod is given, it's d. So this distance will be d minus x. And since you are below the neutral axis, it's a negative y. So you multiply by minus d minus x. And then you will get an equation with just one unknown. So this is the final equation you get. Bx, which is a1, times x over 2, which is y1, equals to nas, which is a2, times minus d minus x, which is y2, equals to 0. B is given, okay? As is the cross-sectional area of steel, you can calculate it. N is the ratio of the modulus of elasticity of steel to the modulus of elasticity of your concrete. And then the only unknown in this equation is x, you got it. This is how you determine the position of your neutral axis. And as you can see, you'll get a second degree equation. And this second degree equation will have two solutions, but one will be rejected because you have x is between 0 and d. Okay, so if you obtain a negative value of x, it's rejected. If you obtain a value of x larger than d, it's also rejected. So you select the appropriate solution for your second degree equation. And once you get x, then you know where is your neutral axis. You know which part, this part will support compression. You can calculate then accordingly the, if you want, the value of the maximum bending moment you can sustain, as we did before. The same will apply for steel. Now we'll do together several problems to practice on this. Okay, so, and as usual, when you calculate the normal stress in concrete and steel, for concrete n is 1. You don't have to multiply by anything, you just apply the formula. For concrete, you have compression. It's equal to minus my over I, and the maximum value of compression will take place at the top, which is corresponding to the distance x. And concerning steel, since it's a modified section, do not forget to multiply by n, which is E steel over E concrete. So you multiply, you do n times m times the distance will be d minus x, because here this is, you consider that this area is located at one level because you have a very small thickness. So it's m times d minus x over, of course, the cross-sectional area I, the cross-sectional area of your modified section will allow you to calculate the value of I. So keep in mind that I is the inertia about the neutral axis of the modified section. Okay, so this is how you can see what is the amount of stress, the maximum amount of stress of compression to which concrete is subjected, and the amount of tensile stress to which your steel is subject. And of course, based on the maximum allowable values, you select what is the maximum bending moment that I can apply to my system. Now, another important idea also in this chapter is to know that we can face stress concentrations when we have sudden change in cross-section. So whenever you are doing a design, in general, we always design based on critical values. So if you have variation in cross section, then you will select the one that is the most critical. Okay. So for example, if you look at this cross section, you have a sudden change in thickness. Okay. And therefore, you have what we call at this level, you will have what is called stress concentration. So stress concentrations will occur in the vicinity of points where the load are applied, and in case we have sudden changes in cross section. So whenever you have a sudden change, this will lead to a non-uniform, if you want, stresses, and you will have like concentration, stresses will be concentrated uh, in certain parts, which are the critical parts. So here, of course, the critical section will be just the one at the sudden change in cross section, and you will take, of course, the smallest cross section. So the maximum stress will correspond to the value of